my first antinode. I go another quarter wavelength to my second node, if you like, and so on. That's my third quarter. Well, that's where I got 3 quarters from, right? If it had actually been closed on this side here, that would have been 4 quarters. It would have been exactly 1 cycle. But because it's open here and closed here, I only make it 3 quarters. So the way I get these things is by looking carefully at this picture and drawing a careful picture. That's the way I always solve them. Does it make sense? You don't like it? I would say these are the sort of cases you're going to see, so it's good to be familiar with this and to draw them and sort of check it out, make sure you're comfortable with it, but and to know what situation results in these different things. But to get these things right, I just draw a careful picture and count quarter wavelengths. Because it's always some number of quarter wavelengths. Because whether you've got a node or an antinode at the end, you're going to be at a quarter wavelength, some multiple of quarter wavelength from the end of the pipe, or the rope, as it may be a rope. Either way. Okay, so good. We played some sounds out there and agreed with what we found with the equations in our pictures. This is the way to think about it. I told you I was going to talk about traveling versus standing waves. I did it in the context of that example. Let's do one more example of traveling versus standing waves. If I want to talk about the standing wave, let's say the fundamental, for example. Suppose I want to explain how can I think about this fundamental. I'll use our blackboard here. This fundamental. It looks like this, the standing wave, going up and down like that. How do I think about that in terms of standing, in terms of traveling waves? Well, that's just equal to this traveling wave. Actually, it's probably smaller. It's a shorter traveling wave. I need 2 of them that are half the same height. So I'll take one that goes like this, and it's going that way, say at some velocity v. Well, and then below that, let's add on one that's going the other way. And right now, let's have them lined up. So right now, they're perfectly lined up. What's different about them is they're moving in the opposite direction. So he's going to the left, he's going to the right. And what height is this? That height is 1/2 the amplitude of my standing wave. Right? So this distance is A. That's my amplitude of my standing wave, right? And I say, well, if I have 2 waves that are opposite in direction but equal in height, both equal to half the original amplitude, right? If I add them together, well, you can see what happens. If I add these together, I'm just going to wind up with a bigger sine wave, right? It's taller. And if we say this is where we're going to think of, let's think of this point and this point as the wall. So this is x equals 0. Here's my x equal L, right? So here's x equals 0 here, and then L. So here's my x-axis, right? Yeah, here, I'll do it this way, L and 0. If I do that right. So what am I drawing here? I'm saying let's take these 2 things out together. Well, if I add these together, it works. I get this upward guy right here within this region. I get the upward going rope. But what happens later? Well, a little bit later, here I'll use a different. I don't have different colors, do I? They get so busy with all the different pictures. I'm just going to go ahead and draw. Here, I'll do this. Some kind soul left me their color shot collection. So I'm going to go ahead and take this blue chalk. Hopefully it'll show up as a little bit different. If this guy's moved over a little bit, what happens? Well, now he looks like this, right? And this guy's moved that way by the same amount because the speeds are the same. They're going in the opposite direction. So he's going like that, right? So if I add those together, what do I get? Well, just like in the example we had over there at the wall, the wave is moved over. It's got some positive, little small positive value, a little bit less than a over 2, right? But this has a small negative value and exactly cancel out. So if I add those 2 guys together, I'm still at 0 on the ends. In fact, on the right side, I'm still at 0 because on the right side, the upper guy has gone taller at that point, but this lower guy has gone lower. So if I add those together, I'm still at 0. Initially, I was at the full height of A. It was like this, right? Where that height is A. But now that these waves have moved over a little bit, they're a little bit, the interference between them, right? When I add them up, it's got a little bit of destructive interference going on. Because this is fully destructive interference. That's why you got 0 at the ends. And if I go through all the math at the middle, I find, well, I'm a little bit shorter than I used to be. This was my tallest points right in the middle before, right? When you guys were exactly lined up. But now that the wave moved a little bit later in time, I see that it's a little bit shorter. And same thing here, it's a little bit shorter. The result is you get this. You get the same shape, but it's shorter a little bit. And I hope that was clear. But if I go through this, I'll use the other color, and I'll draw a few more. If I keep doing this, I keep drawing examples of these waves move further over, I'll eventually get to a point where they're exactly canceling out. When the 2 waves are exactly out of phase by 180 degrees. When they go a little further, that starts to keep moving around like that, and then eventually comes back to the full value the other way. That's when the waves are lined up again, but now both of them are going down inside this space. So the result is that this wave that's just going up and down, the standing wave, you can think of it as the sum of 2 traveling waves that are equal and opposite in their directions and speeds, right? And they have both 1/2 the amplitude, each of them, compared to the amplitude of the resulting standing wave. So anyway, linear superposition. And traveling waves and standing waves, they're really just manifestations of the same phenomenon. You can add a couple of them together to get a couple of the traveling waves together to get a standing wave. All right, let me just check my, oh yes, one more musical instrument thing to talk about with standing waves, and that is a xylophone. So the trick with this stuff is to figure out which of these situations is relevant to whatever instrument or whatever object you're talking about. With a rope, you're tying it down on both sides. Okay, this is what you want. You know, you have a pipe organ, it's closed on both ends. Okay, this is the sort of things you want. Open on one side, closed on the other. Okay, open on both sides. What about a xylophone? So, yeah, see, so xylophone, right, you know what that is. These make very nice, the timbre, oh yeah, what's timbre? Timbre, different instruments sound different. They have different timbre. Why is that? Well, if I play the same note at the same intensity, so it's the same loudness at your ear, you're listening, you can tell whether it's a trumpet or my voice or a xylophone because of the relative amount of power that's distributed amongst the higher harmonics above the fundamental. So when I say that they have the same pitch, or the same note is being played, what do I mean? I mean that if I play a note from a trumpet or I play a note from the xylophone, they're the same pitch. It means that the fundamental wavelength is the same. But what's different is how much power is distributed among the higher harmonics, right? And what you can see here is that like the harmonic structure here and here would be somewhat similar in that the same sort of frequencies are present, right? You get the same frequencies. The relative power here might be different though, depending on the physics of the problem. It's a little beyond the scope of the class, but you might be told some harmonic structure. You might be told, oh yeah, the first, well, lambda 2, like the volume from lambda 2 is going to be half as much, or the amplitude of the wave will be half as much as you got from lambda 1. Whereas for smaller instrument, with the same set of frequencies that are possible, maybe it'll be 3 times smaller instead of 2 times smaller. So the number and the relative strength of those higher harmonics, that's what determines what makes different sounds sound different. Different instruments sound different, even when they're playing the same volume and the same note is being played. Now a xylophone, which of these pictures corresponds to the xylophone? Well, take a look. I don't know if you can see it in the big picture. Oh yeah, great. So where do they put the nails? On a xylophone, you don't put the nails at the end, and you don't put them in the middle. You put them right here and here. And that reminds me to talk about baseball, too. So in baseball, it's also true, harmonics play a big role in baseball. So how many of you I've had this experience, you hit a ball with a bat, and it hurts like heck, right? If you hit the ball in the wrong part of the bat. Why should that be? You hit the sweet spot of the bat, doesn't hurt your hands, right? And the ball goes really far and you feel good, right? You hit the wrong part of the bat, and it hurts like heck, and the ball doesn't go so far, so that's not good. So what's going on? When it doesn't go so far, actually, I shouldn't say that. It can still probably go pretty far, but it doesn't go any further for all the pain you sustain, right? So why is that? Actually, yeah, I take it back. It doesn't go as far, but for reasons I'm not going to mention. I'm just going to mention the part about the oscillation. So the xylophone and a baseball bat are both similar types of instruments, if you will, and that the vibrational mode is that they wiggle back and forth. They go like this. So the fundamental mode of vibration for a xylophone is like this. I'm really exaggerating it here. It goes like that, and it goes like that. So it's wiggling back and forth, right? Oh, here, maybe I should do it this way. I'll draw it like this. I'll draw it like this. So if the center of mass doesn't move on the thing, if it's just wiggling back and forth, the center of mass just stay put in the middle. When it goes like that, center of mass is right there. It goes like that, center of mass is right there. It's just going like a bird, flapping back and forth. That's what those xylophone pieces are doing when you strike them with a mallet, right, or a little, what do you call that thing, a little drumstick. It does this, and this is where you put the screws right over here and right over here. It allows the ends to move freely, and it'll move a little bit. This is the fundamental mode of vibration. This is the lowest frequency mode of vibration for xylophone. For a baseball bat, it's like this. I'm really exaggerating. Here's your slugger bending around the ball. So, you know, bang, right? You hit the ball. If the ball's going that way, the bat wraps around the ball a little bit. Not this much. I really exaggerated it. But that's the motion it makes. Now, if you hit the ball over here someplace, then you excite high-frequency modes. You excite modes that look like this. You know? So if you hit the ball near the end of the bat, you excite this mode of vibration a little bit, but you excite these other higher, as you know, if you have more nodes along the length of it, it corresponds to higher frequency. That's what we found with the rope. We found with the, over here with the wind instrument, or what we call it, the pipe organ, right? Same thing's true for a baseball bat. So the reason it hurts when you hit the ball in the wrong spot is that you've excited the higher harmonics that correspond to high frequency. So the reason it hurts is it's shaking really fast back and forth, and it hurts your hand. When you hit the sweet spot of the bat, most of the energy that goes into vibrational modes of the bat, most of it's in the lowest frequency mode of vibration, and that's slower, and it doesn't hurt as much. So that's essentially what's going on. Anyway, to help you think about this, I was sort of surprised when I found that out. But anyway, that's the truth. So that's why you aim for this part of the bat. It's also the case that if you hit it like this, the center of mass of the bat is pretty well lined up with the ball. So you don't wind up torquing the bat so much. You wind up putting a lot more energy into the kinetic. The ball winds up going forward instead of bending around like that, right? So that's the reason why you hit the ball at the right spot. The ball goes forward. But that's aside. That's a separate issue. Anyway, and then when it comes to this kind of stuff, the way physicists solve these things, or engineers, think about it, they'll use, again, Fourier decomposition. Any weird shape this bat might take, because what it really looks like isn't like this. I'm just drawing one mode of vibration. The bat really looks like this. Here's the ball, here's the bat, and here it is way at the end. You can write that funny shape as a sum of sine waves. One of them looks like this, one of them looks like that. There's a bunch of others. Any shape you make the bat take by banging the ball on some funny part of the bat, you can represent as a series of sine waves. And the closer that kink is to the end of the bat, the bigger the amplitude of these high frequency ones. So that's sort of Fourier analysis in the context of music and baseball. You don't have to do a lot of Fourier analysis in this class, but it's good to understand. It's good to have a feeling for where the frequencies are higher or lower. You'll save time on the exam if you got some common sense about. I shouldn't call it common sense. You have some good intuition about these sort of ideas about which correspond to higher frequencies and lower frequencies. And so that's why they put the screws where they do on the xylophone. It results in not damping out the sound right away. It allows it to keep vibrating that way, and you get a nice long ringing tone that doesn't die off right away. So, all right. So if you have a xylophone, oh yeah, so if you want to calculate for a xylophone, what's the right? Which of these pictures is correct? It's actually the open on both ends picture. This really is the vibrational mode you're talking about for the xylophone. So if you want to know what the frequency was as a function of the wavelength, and you know how long the piece of metal is and stuff, this is a good approximation to what you're getting for your fundamental. Right? Not although you get the same number numerically here as that, but it's not like this, right? It's like this. Okay. Oh, that is a great question. Am I putting you on? I might be putting you on. That's a great question. So yeah, this is where the screws are, right? In fact, yeah, of course you're right. You're exactly right. And there's two reasons we know that. One is because I kept telling you about the screws and I ignored my own advice. But there's a second reason, and that is that this is not the picture I was drawing over there, right? This is going like this. You're not going to do that unless. So if I put a screw in the middle and nail it, yeah, that's a fantastic question. I apologize. You got that right the first time. But yes, this is the right mode because this is possible. If you have a freestanding piece of metal, it can do this. It can flap up and flap down. But it's not going to do this. That requires something in the middle that's torquing it back and forth. So you're absolutely right. This isn't the right one to look at. It's the right physical situation that it's free on the ends, but it's not right in the middle. And in fact, I even drew the picture right there where you can see it wiggling up and down. No, so you think I look at my own drawing. But yes. So yeah, make careful drawings and keep your wits about you. Whether you're under scrutiny by people watching you or you're on a test. Yeah, don't do foolish mistakes. You can always recover though. That's what I say. Although I don't always recover by the end of the lecture. But this time somebody help me out. That's good. Don't work on the exam. All right. So very good. So that's exactly right. So this is the one to think about for xylophone. That's right. Except for two reasons. Okay, good. So I think that brings us. Oh, there's one more topic. And it's the Doppler shift. It's a very important topic. So waves. There's two kinds of Doppler shifts, broadly speaking. There's actually many kinds, but there's two broad categories, and they have to do with whether the source or the observer of the wave is moving. So suppose you've got a moving source. Okay, so you're in some old 60s movie with the actually forget the 60s. What matters is this in England. So in England, there's this characteristic sound of the cop car when it's coming or receding, right? And it sounds goofy. But I'll go ahead, right? So it's going to and it passes by, right? It falls off. Well, what's going on is it's a Doppler shift. The bad guy who's hiding in the phone booth or whatever is holding still, and the car is approaching, and then it's receding, right? This is a case where the person who's listening is holding still. Right? He's holding still. He's holding still with respect to the air. That's the medium within which the sound wave is traveling, right? So he's holding still. The cop car's coming, and the frequency is higher as it approaches, and it's lower as the car goes away, as the source recedes. So let's draw a picture of what that looks like. If you're holding still, this is a picture of what the sound waves look like coming out from some police car that's holding still. And all I'm doing is I didn't do a perfect job of while you're here. I meant to draw these exactly concentric. These are supposed to be concentric circles, and these circles represent surfaces of constant, whatever it is, air displacement. You know, so the longitudinal wave. If I make sound from a siren, the air's doing this, right? Well, these are traveling waves, not standing waves. They're traveling outward at some velocity v, right? Based on it's like 300 meters per second for speed of air, right? Excuse me, speed, not speed of the air, speed of the sound in the air, the wave speed. And then there's also some wavelength associated with it. Now the wavelength depends on exactly what frequency and this thing's oscillating at, right? It's the siren. But whatever it is, it produces some wavelength lambda. And let's assume that it's a perfect sine wave. That it's a single frequency. It's not like it's not a complicated piece of music. It's just a single frequency. So in that case, somebody standing back here and somebody standing over here will hear the same frequency. Now the police car is moving. And we have a bunch of things moving now. We'll have wave speed and we'll have a moving source. So let's give different names to these. The names of the book is, the symbols of the book use, it uses u for the velocity of the source and v for the wave speed. So I'll stick with my convention v as wave speed as I've already been using it. What does that look like? Well, if this cop car is moving to the right, at speed u. So it's going this way at speed u. Oh, sorry. Let's write it u. It's a downward serif, right? U. Okay, it's going that way. What does that look like? Well, when he released his first sound wave, he was over here someplace. Right? And then expanded outward. So like this guy, this wave that was released a while ago, that's back when he wasn't here. He was back over here somewhere. So that looks like this. And the one he released a little bit later, it was released when he was over here. Right? And the one that was released a little later, it was over here. And the one he released just a couple seconds ago, it was over here. So you can see what's happening. When a source is moving inside the medium that carries the wave, inside the air, so the car's moving, right? The waves bunch up in the front and they get spread out in the back. So this is bigger than lambda, that's smaller than lambda. Okay? And the Doppler effect is just this. Someone who's listening. So suppose you've got some observer, we'll call them observer A over here and observer B over here. I think that's the way the book labeled them. If they're holding still, like a bad guy waiting in the phone booth, as the car approaches, he hears this. He hears the wave fronts coming more rapidly than you'd expect with the car holding still. That gives it a higher frequency. That's a higher pitch he hears, right? And so if we go through the math and figure out for a moving source, we figure out what the change is going to be for the frequency, well, you say, all right, well, what is the wavelength going to be for this observer? What does he experience? He experiences a wavelength that is equal to, let's say, we'll call it, this is the observer's experience for observer A, right? What does he experience? Well, he gets a wavelength that is going to be smaller than the original wavelength. It's whatever the wavelength would have been minus the amount of distance the car traveled, right, between these wavefronts, right? So what does that look like? It looks like minus u times lambda over v, if I've got my u's and v's straight. I think I've got this right, but keep me honest here. So this says that if u, so let's check a limit real quick. If u is equal to 0, the car's not moving, then we get the expected answer. Lambda prime equals lambda. That makes sense. If u is positive and the guy is in front of the car, which is what I want, then lambda get prime is smaller than lambda. That's correct. It's a positive number, you subtract it. Good, that makes sense. The bigger u is, the more you subtract off. It's proportional to u, and that makes sense. The faster the car's going, the more he's moved over before he produces his next wavefront. And you notice in terms of units, it makes sense. You have velocity over velocity, so the units of those guys cancel out. You're left with a wavelength, and wavelength makes you a wavelength. So that's good. So we can rewrite this. You say, oh, that's just equal to lambda times 1 minus u over v. And notice that if the speed of sound is really fast compared to the car, then this is a very small effect. But if the speed of the car is huge compared to the, or let's not say huge, let's say it's almost as fast as the speed of sound, it's a huge effect. The wavelength almost goes to 0. So this is the relationship for what you get in terms of the wavelength. If I want to know about the frequency, then I just take 1 over this relationship, right? The new frequency, let's not say A, let's just do it for both. You do the new frequency, what is it equal to? It equals the frequency you would have gotten from the original source if it were just, what is its frequency, its oscillation frequency, and divide by 1 plus or minus u over v. The plus corresponds to this, let's see, no, the minus corresponds to this situation. So minus is for approaching, right, if I've got my signs right, corresponds to that picture, and the plus is for receding. Check my sheet, make sure I told you the truth. Well, I didn't even write it on my sheet. We can figure it out. If it's plus here, then you get a bigger thing at the bottom, and that means that the frequency here is smaller. So that's what you get going away from you, and that's what I wrote. See, good, I got the sign right. Does everyone see that? In other words, it's the opposite sign I had. Excuse me, same sign here, but now it's the denominator instead of the numerator. This frequency has the opposite effect as wavelength. Okay, great. So this is the formula for a moving source. But what if the listener is moving? It's a different physical situation. I might surprise you. So I'm going to put a little box around this section and say that's all the same thing I'm describing. Oh, and I just lumped it all together. I'm talking now about either B or A, where B is the guy for approaching, excuse me, A is the one for approaching and B is the one for receding. This is a single formula that embodies both of those ideas. But the idea is the same. The reason for it is the same. The wavelength is longer here, it gets shorter there. If you think about a moving source, let me see one more thing about this. Suppose I move exactly the speed of the wave in the medium. Suppose the cop car was moving at the speed of sound, right? If that were true, you wouldn't hear him coming, right? Until he runs into you. Or until he passes you by and you get hit with, what's that called? Yeah, it's a shock wave. We call it sound shock wave. It's a sonic boom. That's right. And the thing is, people think, oh yeah, sonic boom happens when you cross the threshold of going just below to just above the speed of sound. That's not true. The shock wave actually occurs for anything that's moving at the speed of sound or greater. And it looks like this. Suppose this guy's moving, suppose u is bigger than v. Well, then these little circles are no longer, they're like this, right? The wave fronts are like that. They're no longer contained inside themselves. So you get this shock wave. And the person whose ear is right here, right, he's hearing the shock wave. When this thing goes by, you hear a sonic boom, bang, right? There's all this air that's crammed up together that goes by, and the pressure is really huge, goes by your ear, and you hear the sonic boom. So we hear sonic booms when things fly faster than the speed of sound because of the shock wave. Same thing for the wake of a boat. So a boat travels faster than the speed of waves on the surface of the water. If it's going faster than its hull speed, I guess it's called, then you get these waves, this wake that looks the same way, an edge, this sort of wedge shape off the front of the boat. Same thing. It even happens with light. In fact, when I was an undergraduate, I built part of a detector that I used at SLAC for the Stanford Accelerator Center for detecting fast-moving particles that were moving faster than the speed of light inside the medium. You got some medium that had a very high index of refraction, which tells you how fast light can travel. Light in a vacuum. You can't go faster than light in a vacuum, as far as physicists know. But you can go faster than light if you're inside of some freon liquid or some stuff with a high index of refraction, or diamond or glass or something. And sure enough, that's what happened. You get a photonic boom, if you like, as somebody called it. You should have called it that. You get this wake that was light coming off of this particle that's going faster than the speed of light, and that's called shrink radiation. Anyway, so there's lots of examples of shock waves, and moving sources in some wave-producing medium are important. It comes up a lot. Right? And here's the formula for calculating what the frequency would be. Notice if you have u bigger than v, and you're subtracting, so you've got an approaching source, you get a negative f prime, a negative frequency. But in that case, you're not going to hear anything because of the physics. So it doesn't matter what this is doing. When you think about it, if this guy's traveling faster than speed of sound, then you're not going to hear an approaching source. This is only a useful formula for a receding source in that case. And for a receding source, that's the plus sign over here. Well, you can add as big. This would be Mach 3. It's a factor. This would be a factor 3 here. Mach just means how many times the speed of sound you're moving. So that would be a 3. So you get 4. So it's f of 4. So it's a quarter of the frequency. It's really low pitch compared to the sound of the engine of that plane if you were hearing it and it's holding still. But you'll still hear it. It's receding from you, right? Anyway, so what about a moving observer? So that's actually I can keep this picture, can't I? So for a moving observer, that's kind of convenient. Look at the board management I came up with. Pretty good. So this is a case where the source is holding still with respect to the medium that's carrying the wave, the air. The cop car is holding still. But now I'm in a car and I'm either moving toward the police or away. In my case, I'm always going toward the police. So I'd be over here, right? But some of the more exciting lifestyle is going away from the police. So let's have this, right? Let's see. I want to make sure I'm drawing the same way as the book did for what they called A and B. I think I did the way they did. Just so your formulas look the same. You always can figure it out, right? But anyway, so in this case, it's a still source. You've got moving observers, they're called. Even though they're listening, they're not observing, but we call them observers. And we say, what's going to happen? Well, you can tell. Is the frequency going to be higher or lower for the guy who's moving away from the source? Well, yeah, it's going to be lower because he has to catch up with. It's going to take him longer if he just held still, right?